There is a star in our galaxy that defies everything we think we understand about how large celestial objects can grow. A star so enormous that if you replaced our Sun with it, the star's surface would swallow Mercury, Venus, Earth, Mars, Jupiter, and extend somewhere near Saturn's orbit. Light traveling at 670 million miles per hour would need more than 6 hours just to make one trip around this star's circumference. This is not theoretical. This is not an estimate based on indirect measurements from distant galaxies. This star exists in our own Milky Way, close enough that we can study it in detail, far enough that the light reaching our telescopes tonight left that star around the time humans first domesticated dogs. VY Canis Majoris contains a volume so vast that you could fit over 7 billion of our suns inside it. It shines with the intensity of 270,000 suns burning simultaneously. And perhaps most unsettling of all, this star is dying. Dying in a way that violates the gentle narrative we usually tell about stellar death. This star is not quietly fading. It is violently ejecting its own substance into space at rates that challenge our models of how stars should behave. For decades, astronomers have debated whether VY Canis Majoris truly deserves the title of largest known star. The measurements are difficult. The star itself is so extreme that it breaks the tools we normally use to study distant objects. But what is certain is this. VY Canis Majoris represents something at the absolute edge of what stellar physics permits. A star so large that understanding it has forced us to rewrite fundamental theories about how matter behaves under the most extreme conditions. If you appreciate explorations that challenge the boundaries of human knowledge, hit that like button and subscribe. What we are about to examine will permanently alter how you see every star in the night sky, because if nature can produce something this impossibly large, what else have we failed to imagine? Let's begin. The story of VY Canis Majoris begins not with modern telescopes or sophisticated instruments, but with a French astronomer named Joseph-Jérôme Lefrançois de Lalande, observing the sky in the year 1801. March 7th, to be precise. Lalande was conducting one of the most ambitious projects of the early 19th century, cataloguing the positions of every star he could observe from his observatory in France. Lalande would eventually catalogue over 47,000 stellar positions, a monumental achievement for the pre-photographic era. Each observation required him to carefully measure angles, record times, and perform tedious calculations to convert his observations into standardized coordinates. The work was painstaking, repetitive, and absolutely essential for the development of astronomy as a science. On that March evening in 1801, Lalande recorded a star in the constellation Canis Major, the Great Dog. The coordinates he noted corresponded to what we now call VY Canis Majoris, though at the time it was simply one more data point among thousands. Lalande noticed nothing particularly unusual about this star. It appeared as a dim reddish point of light, unremarkable compared to the brilliant stars that dominate Canis Major, especially Sirius, the brightest star in Earth's night sky. But Lalande did note something curious. When he returned to this same region of sky years later to verify his measurements, the star's brightness had changed. The object that had appeared at a certain magnitude in 1801 now shone either brighter or dimmer. He was not entirely certain which, because his earlier notes were incomplete. This variability marked VY Canis Majoris as worthy of additional attention, even if Lalande did not realize the full significance of what he had found. The 19th century marked a revolutionary period for astronomy. Telescopes were growing larger and more sophisticated. Photography was beginning to replace the human eye as the primary tool for recording celestial observations. Spectroscopy, the technique of spreading starlight into its component colors to reveal chemical composition and physical conditions, emerged as a powerful new method for studying stars. These advances would eventually reveal that VY Canis Majoris was far more than just another variable star. In 1847, the German astronomer Johann Franz Encke studied VY Canis Majoris in detail. Encke was director of the Berlin Observatory and one of the most respected astronomers of his generation. He noted the star's deep red color, visible even through modest telescopes. This color immediately told Encke something important about the star's nature. Stars come in different colors depending on their surface temperature. Hot stars burn blue or white. Think of Sirius or Rigel. Medium temperature stars like our Sun appear yellow or white. Cool stars glow red or orange. The deep red color of VY Canis Majoris indicated surface temperatures far below average. But color alone could not reveal whether this was a small, cool star relatively nearby or something more exotic. What Encke also observed, and what truly distinguished VY Canis Majoris from ordinary red stars, was the extensive nebulosity surrounding it. Through his telescope, the star appeared embedded in a faint glow, a cloud of material that extended well beyond the stellar disk. This nebulosity suggested the star was losing mass into the surrounding space, creating an envelope of gas and dust that scattered and reflected the star's light. 19th century astronomers had no framework for understanding what this nebulosity meant. They could describe what they saw, but the physical mechanisms driving such extreme mass loss lay beyond the theoretical capabilities of the time. It would take more than a century of advances in physics, nuclear chemistry, and observational technique before astronomers could begin to comprehend what VY Canis Majoris actually was. The location of VY Canis Majoris in Canis Major places it in one of the richest regions of the night sky for observers in Earth's northern hemisphere during winter months. Canis Major, the Great Dog, is one of the 48 constellations catalogued by the Greek astronomer Ptolemy in the 2nd century CE. The constellation appears to follow Orion the Hunter across the sky, with Sirius marking the dog's head or heart depending on which cultural interpretation you follow. To locate VY Canis Majoris, you first find Orion, easily recognizable by the 3 bright stars forming Orion's belt. Follow the belt stars downward and to the left, and you will find Sirius, unmistakable as the brightest star in the sky. VY Canis Majoris lies about 10 degrees southwest of Sirius, though you will need optical aid to see it. At magnitude 7.4 on average, the star hovers just below naked eye visibility. Under perfect dark sky conditions with excellent eyesight, some observers might glimpse it, but most will need binoculars at minimum. Even through a telescope, VY Canis Majoris does not appear particularly impressive to visual observers. It shows as a reddish point or slightly fuzzy patch depending on the instrument and atmospheric conditions. The true majesty of this star reveals itself only through long exposure photography and spectroscopic analysis, techniques that accumulate light over time and analyze wavelengths invisible to human vision. The distance to VY Canis Majoris has been refined repeatedly over the decades as measurement techniques improved. Early estimates in the mid-20th century ranged wildly, from as little as 1,500 light-years to as much as 5,000 light-years. This threefold uncertainty made calculating the star's physical properties essentially impossible. If you do not know how far away something is, you cannot determine its true size or luminosity, only how bright it appears from Earth. Modern measurements using data from the Hipparcos satellite launched in 1989, and especially from the Gaia Space Observatory launched in 2013, have narrowed the distance estimate considerably. The current best estimate places VY Canis Majoris approximately 3,800 to 4,900 light-years from Earth, with most analyses favoring a distance near 3,800 light-years. To grasp what 3,800 light-years means, Consider that light travels at approximately 186,282 miles per second, or about 5.88 trillion miles in 1 year. Multiply that by 3,800,000, and you get roughly 22.3 quadrillion miles. That number is so large it loses all intuitive meaning. Better to think of it in terms of travel time. Our fastest spacecraft, the Parker Solar Probe, reaches speeds near 430,000 miles per hour when diving close to the Sun. At that speed, which no other human-made object has approached, the journey to VY Canis Majoris would require approximately 5.9 billion years. The Earth itself is only 4.5 billion years old. The entire history of our planet, from molten ball to the present moment, would not be enough time to reach this star even at humanity's fastest speeds. This distance places VY Canis Majoris firmly within our galaxy. The Milky Way stretches approximately 100,000 light-years across, meaning VY Canis Majoris lies roughly 4% of the way across the galaxy from our position. By galactic standards, this is relatively nearby. Many stars we study lie tens of thousands of light-years away. VY Canis Majoris is practically in our cosmic neighborhood, which makes it all the more valuable for detailed study. The constellation Canis Major lies in a direction that looks toward the Milky Way's disk, rather than out toward intergalactic space. When you observe this part of the sky, you are looking through the thickness of our galactic disk, seeing thousands upon thousands of stars piled up along the line of sight. This creates both opportunities and challenges for studying objects like VY Canis Majoris. The opportunity is that the region contains many interesting objects to study within relatively close range. The challenge is that foreground and background stars can confuse observations. Additionally, the line of sight to VY Canis Majoris passes through regions of interstellar dust that absorb and scatter starlight, making the star appear dimmer than it would if observed through clear space. Astronomers quantify this dimming effect using a measurement called extinction. VY Canis Majoris suffers approximately 2 to 3 magnitudes of visual extinction, meaning it appears roughly 10 times dimmer in visible light than it would without intervening dust. This is substantial, but not catastrophic. Some stars in dusty regions suffer extinctions of 10, 20, or even 30 magnitudes, rendering them completely invisible at optical wavelengths. For VY Canis Majoris, the extinction is manageable, especially when observing in infrared wavelengths, where dust is more transparent. Modern studies of this star rely heavily on infrared observations that penetrate the dust and reveal details invisible to optical telescopes. This technological capability, developed primarily in the late 20th century, has revolutionized our understanding of cool, dusty objects like VY Canis Majoris. The recognition that VY Canis Majoris was not just unusual, but genuinely extreme developed gradually over the 20th century as astronomers accumulated more data and refined their analytical techniques. By the 1970s and 1980s, spectroscopic studies had revealed the star's enormous luminosity and cool temperature, indicating an object of exceptional size. But precise measurements of stellar diameters for distant objects remained extraordinarily challenging. In 1976, astronomer Charles J. Larder and colleagues published observations of molecular emission from materials surrounding VY Canis Majoris. They detected molecules including water vapor, silicon oxide, and various carbon and nitrogen compounds. The presence of these molecules confirmed that the star was losing mass at prodigious rates, creating a complex chemical environment around itself. Through the 1990s and 2000s, improved imaging techniques using interferometry began to resolve VY Canis Majoris as an extended object rather than a simple point of light. Interferometry combines light from multiple telescopes to create an effective aperture much larger than any single telescope, achieving angular resolution sufficient to measure the apparent sizes of nearby giant stars. In 1998, A team using the Infrared Optical Telescope Array at Mount Wilson Observatory obtained interferometric measurements suggesting VY Canis Majoris had an angular diameter of approximately 14 milliseconds. For comparison, 1 millisecond equals 1,000th of an arcsecond, and 1 arcsecond equals 1/36th of a degree. The full moon spans about 1,800 arcseconds, or 1.8 million milliarcseconds, making it roughly 130,000 times larger in apparent size than VY Canis Majoris. Converting angular size to physical dimensions requires knowing the distance, which, as we have discussed, carries significant uncertainty. Using the currently accepted distance near 3,800 light-years and combining it with various angular size measurements, astronomers have calculated that VY Canis Majoris has a radius somewhere between 1,300 and 1,540 solar radii, with many studies clustering around 1,420 solar radii as a representative value. Let me translate that measurement into terms we might comprehend, though I warn you that intuition fails at these scales regardless of how we frame them. Our Sun's radius measures approximately 432,000 miles, or about 696,000 kilometers. Multiply that by 1,420 and you get a radius for VY Canis Majoris of approximately 613 million miles, roughly 988 million kilometers. The diameter, twice the radius, stretches to about 1.23 billion miles, or nearly 2 billion kilometers. Light, traveling at its constant cosmic speed limit, requires more than 6 hours to traverse this diameter. For comparison, light travels from the Sun to Earth in approximately 8 minutes. VY Canis Majoris is so large that light needs more than 6 hours to cross it once. Consider another comparison. Earth orbits the Sun at an average distance of 93 million miles, 1 astronomical unit by definition. VY Canis Majoris has a radius of approximately 6.6 astronomical units, a diameter of 13.2 astronomical units. If you place this star where our Sun currently sits, with its center at the Sun's position, the star's surface would extend outward to approximately the orbit of Saturn. Mercury, orbiting at 0.39 astronomical units, would be utterly consumed, vaporized deep within the stellar atmosphere. Venus at 0.72 astronomical units would vanish without a trace. Earth at 1 astronomical unit would be obliterated, not at the surface of the star, but deep in its interior, where temperatures reach tens of thousands of degrees. Mars at 1.5 astronomical units would be gone. The asteroid belt, spanning 2 to 3.5 astronomical units, would be swept away completely. Jupiter at 5.2 astronomical units would be swallowed whole, its 318 Earth masses of gas compressed and ionized within the stellar envelope. Only Saturn at 9.5 astronomical units would orbit just beyond the star's photosphere, the layer we define as the stellar surface. But Saturn would no longer orbit a point source sun. Instead, it would circle a glowing red wall that fills most of the sky, a star so vast that from Saturn's perspective, the concept of the Sun as a discrete object in the sky would become meaningless. The Sun would be everywhere, a dim red dome covering half the celestial sphere. And this brings us to the heart of why VY Canis Majoris matters so deeply to astronomy and to our understanding of the universe. This is not speculation about exotic physics in the early universe or theoretical extremes we can never observe directly. This is an object in our galaxy, observable with equipment available to well-equipped amateur astronomers, that somehow exists despite appearing to violate the boundaries of what stellar structure should permit. Before we can understand why VY Canis Majoris is so remarkable and why it has generated so much scientific debate, we need to establish some foundation about how astronomers actually measure the sizes of stars. After all, we cannot physically travel to VY Canis Majoris. we cannot send a probe that will return with direct measurements. Every fact we know about this star comes from analyzing the light that reaches us after a 3,800-year journey through space. How do astronomers determine that a star is 1,420 times larger than the Sun when that star appears as nothing more than a dim reddish point even through powerful telescopes? The answer involves multiple techniques, each with its own assumptions and limitations. And understanding these methods reveals both the power and the constraints of modern astronomy. When you look up at the night sky, every star you see appears as a point of light. This is true whether you observe with your unaided eye with binoculars or even through the most powerful optical telescopes on Earth. The reason has nothing to do with the actual sizes of stars, but rather with their enormous distances combined with a fundamental limitation called the diffraction limit. Light behaves as both a particle and a wave, and when waves pass through an opening like a telescope aperture, they spread out slightly. This spreading, called diffraction, blurs the image of a point source like a distant star. The amount of blurring depends on the wavelength of light and the diameter of the telescope aperture. Smaller apertures produce more blurring. Longer wavelengths produce more blurring. For even relatively nearby stars, the angle they subtend on the sky, their angular diameter, is so tiny that atmospheric turbulence and diffraction effects completely wash out any actual disk. The star appears as a point no matter how much magnification you apply. This is why stars twinkle. They are point sources, whose light gets distorted by turbulent air. Planets, being closer and showing actual disks, twinkle far less. So if we cannot resolve stars as disks, how do we measure their sizes? Astronomers use several approaches, each applicable under different circumstances. The first and most fundamental method uses the relationship between luminosity, temperature, and radius encoded in the Stefan-Boltzmann law. This law states that the energy radiated by an object depends on its surface area and temperature. Specifically, luminosity equals the Stefan-Boltzmann, constant times surface area times temperature to the fourth power. If you can measure a star's luminosity and temperature, you can calculate its radius. The challenge lies in determining luminosity accurately. What we observe directly is apparent brightness, how bright the star appears from Earth. Converting apparent brightness to luminosity requires knowing the distance, because brightness decreases with the square of distance according to the inverse square law. For VY Canis Majoris, spectroscopy provides the temperature measurement. The star's spectrum shows characteristic absorption lines and overall shape that correspond to a surface temperature around 3,000 to 3,500 Kelvin. This makes VY Canis Majoris one of the coolest stars known, far below the Sun's 5,778 Kelvin surface temperature. The apparent brightness can be measured precisely using modern detectors. VY Canis Majoris has an apparent magnitude around 7.4 at visible wavelengths, though it varies over time. But it shines much brighter in infrared wavelengths, where cool stars emit most of their energy. Combining observations across multiple wavelengths allows astronomers to determine the total energy output. The distance measurement introduces the largest uncertainty. As discussed earlier, estimates place VY Canis Majoris somewhere between 3,800 and 4,900 light-years away. This 25% uncertainty in distance translates directly to a 25% uncertainty in calculated luminosity, which then propagates into the radius calculation. Even with perfect distance measurements, applying the Stefan-Boltzmann law to stars like VY Canis Majoris involves complications. The law assumes an ideal blackbody with uniform surface temperature. Real stars have temperature variations across their surfaces, dark spots, bright regions, and extended atmospheres that absorb and re-emit radiation in complex wavelength-dependent ways. For red supergiants and hypergiants like VY Canis Majoris, these complications become severe. The star's extended atmosphere contains molecules and dust that absorb stellar photons and re-radiate them at different wavelengths. The observed spectrum represents a combination of direct emission from the stellar surface and processed radiation from circumstellar material. Disentangling these components to extract true stellar luminosity requires sophisticated modeling. Current estimates place VY Canis Majoris's luminosity around 270,000 to 400,000 times the Sun's luminosity, with the uncertainty reflecting both distance uncertainty and modeling challenges. Using a temperature near 3,200 Kelvin and a luminosity around 300,000 solar luminosities, the Stefan Boltzmann law implies a radius near 1,400 solar radii. Different combinations of assumed temperature and luminosity within observational constraints produce radii ranging from about 1,300 to 1,650 solar radii. A second technique for measuring stellar sizes uses interferometry. This method combines light from multiple telescopes separated by large distances to create an effective aperture much larger than any single instrument. The interference patterns produced when light from different telescopes combines contain information about the source's angular size and structure. The Very Large Telescope Interferometer in Chile, the CARA array in California, and other facilities have achieved angular resolutions down to a few milliarc seconds, sufficient to resolve the disks of nearby giant stars. For Betelgeuse, located about 650 light-years away, interferometric observations clearly show an extended disk with a measured angular diameter, around 40 to 50 milliarc seconds depending on wavelength. VY Canis Majoris has been observed interferometrically multiple times, with varying results depending on the wavelength observed and the analysis technique employed. Observations in the near-infrared suggest angular diameters around 11 to 18 milliarc seconds for the main stellar disk, though the star appears considerably larger when extensive circumstellar material is included. The challenge with interferometric measurements of VY Canis Majoris stems from the star's complex environment. The extensive nebulosity surrounding the star produces scattered light that contributes to the interferometric signal. The star itself displays surface structure with bright and dark regions that change over time. These factors make determining a clean, stellar diameter more ambiguous than for cleaner targets. Despite these complications, interferometric observations provide crucial independent constraints on the star's size. A typical measurement might yield an angular diameter around 14 milliarc seconds. Combined with a distance of 3,800 light-years, 1,170 parsecs, this produces a linear diameter around 13 astronomical units, corresponding to a radius near 1,520 solar radii. Different interferometric studies using different techniques and wavelengths have reported values ranging from about 1,200 to 1,650 solar radii. The variation in published size, estimates for VY Canis Majoris, reflects genuine measurement challenges rather than scientific disagreement about fundamental physics. When you see different sources quoting radii of 1,300 or 1,420 or 1,540 solar radii, these differences stem from different analysis techniques, different assumptions about distance and extinction, and different ways of defining where the surface of such an extended and complex object actually lies. This last point deserves emphasis. Stars like VY Canis Majoris do not have sharp surfaces like planets. The density decreases gradually as you move outward from the core. The photosphere, the layer we usually call the stellar surface, represents the depth where the star becomes opaque to radiation. But for red supergiants, this photosphere is extraordinarily diffuse, more like a thick fog than a solid boundary. Defining where the star ends and space begins becomes somewhat arbitrary. different wavelengths probe different depths. So the star appears to have different sizes depending on which wavelength you observe. Molecular absorption in the outer atmosphere affects some wavelengths more than others. The extensive dust envelope scatters and absorbs radiation, further complicating interpretation. Given all these challenges, the scientific community has converged on a consensus that VY Canis Majoris has a radius somewhere between 1,300 and 1,540 solar radii, with a commonly cited value around 1,420 solar radii, representing a reasonable central estimate. This places VY Canis Majoris among the largest stars ever discovered, competing with several other extreme red supergiants including VY Scuti, Stephenson 2-18, and a handful of others for the title of largest known star. The debate over which star truly deserves the largest designation has consumed considerable attention in both scientific literature and popular science media. The competition between VY Canis Majoris, VY Scuti, Stephenson 2-18, and others reflects not genuine scientific controversy, but rather the measurement uncertainties we have discussed. All of these stars are genuinely enormous. All have radii exceeding 1,000 solar radii, and all push at the boundaries of what stellar physics permits. What we can state confidently is that VY Canis Majoris represents an extreme of stellar evolution. Whether it holds the absolute record or merely ranks among the top 5 largest known stars is perhaps less important than understanding what processes allowed such an extreme object to form and what its existence teaches us about the physical limits of stellar structure. The variability of VY Canis Majoris adds another layer of complexity to size measurements. The star's brightness changes over time, not with the regular periodic pulsations seen in some variable stars, but with a semi-regular pattern suggesting complex internal dynamics. The typical variability amplitude is roughly 1 magnitude, meaning the star can appear about 2.5 times brighter at maximum compared to minimum. These brightness changes could reflect actual size variations as the star expands and contracts, temperature changes as convective cells bring hotter or cooler material to the surface, or dust formation episodes that temporarily increase extinction. Likely all 3 mechanisms contribute to the observed variability. This means the size of VY Canis Majoris changes with time, complicating efforts to assign a single definitive radius. Pulsation periods for red supergiants typically range from hundreds to thousands of days. For VY Canis Majoris, the variability pattern suggests characteristic timescales around 1,000 to 2,000 days, roughly 3 to 5 years. During maximum expansion, the star might reach radii exceeding 1,600 solar radii. During minimum, it might contract below 1,300 solar radii. The commonly quoted value around 1,420 solar radii represents something like a time average size. Understanding the size of VY Canis Majoris provides the foundation for comprehending its other properties and its evolutionary state. But size alone does not capture what makes this star so remarkable. We need to explore the physics occurring deep within this cosmic giant and the violent mass loss processes tearing it apart from the outside. Point a powerful telescope at VY Canis Majoris, and you will see not just a star, but an intricate tapestry of structures surrounding it. Arcs, knots, filaments, and clouds extending across dozens of arc-seconds of sky, glowing red and orange in visible light, brilliant in infrared, invisible in ultraviolet. This is not background material unrelated to the star. This is the star itself, or rather what the star used to be. VY Canis Majoris is surrounded by a nebula spanning approximately 120 arc-seconds across, roughly 0.03 degrees on the sky. At the star's distance near 3,800 light-years, this angular extent translates to a physical size around 2 light-years in diameter. For context, The nearest star to our Sun, Proxima Centauri, lies 4.2 light-years away. The entire nebula, created by VY Canis Majoris, spans nearly half the distance to our nearest stellar neighbour. This nebula consists of gas and dust that has been ejected from VY Canis Majoris over the past several thousand years. Doppler shift measurements of spectral lines from different parts of the nebula reveal expansion velocities ranging from approximately 20 to 50 kilometers per second. Material moving at 30 kilometers per second covers about 0.03 light-years per thousand years, suggesting the most distant visible structures were ejected from the star perhaps 50,000 to 100,000 years ago. The total mass contained in this ejected material has been estimated through modeling that considers the density distribution, dust properties, and observed emission characteristics. These studies suggest the nebula contains somewhere between 0.5 and 2 solar masses of material. The uncertainty reflects challenges in determining how much material exists in regions that emit weakly or remain completely undetected. To appreciate what these numbers mean, consider that this mass represents material lost from the star within the past 100,000 years at most, more likely within a much shorter time frame. VY Canis Majoris has shed between 1/2 and 2 times the Sun's entire mass in what amounts to a cosmic eye blink. Our Sun loses mass through the solar wind at approximately 1.4 million metric tons per second. This sounds enormous, but represents only about 9 times 10 to the power of -14 solar masses per year. Over the Sun's entire 10 billion year lifetime, this mass loss will amount to roughly 0.01% of its total mass. The Sun will lose 1/10,000th of itself over billions of years. VY Canis Majoris appears to lose an entire solar mass every few tens of thousands of years. Mass loss rate estimates range from roughly 10 to the power of -4 to 10 to the power of -3 solar masses per year, depending on methodology. Taking a central value around 3 times 10 to the power of -4 solar masses per year, the star ejects approximately 300 Earth masses per million years. Let me express this more viscerally. The star loses the mass of Earth approximately every 6 to 10 years. Everything you see around you, every mountain and ocean, every building and person, the entire planet's mass, represents 6 to 10 years of mass loss from VY Canis Majoris. The star sheds Earths like dandruff. If you could somehow observe VY Canis Majoris continuously over decades, you would watch plumes and streamers erupting from the surface and flowing outward into space. You would see dark dust clouds condensing from cooling gas, blocking light from the star behind them. You would observe glowing arcs and shells of previously ejected material, lit from within by stellar radiation. The star would appear surrounded by a dynamic, churning envelope in constant violent motion. The structure within the nebula reveals that mass loss from VY Canis Majoris is not smooth and continuous, but episodic and highly directional. High-resolution imaging shows distinct features, including multiple arc systems, discrete knots of material, and filamentary structures distributed asymmetrically around the star. One prominent arc structure lies approximately 11 arc-seconds from the star, corresponding to roughly 0.07 light-years at VY Canis Majoris' distance. Proper motion measurements, which track movement across the sky over years of observation, indicate this arc expands outward at roughly 35 kilometers per second. Working backward, this arc was ejected approximately 600 years ago, around the year 1400 CE in Earth's calendar. Of course, the light from that ejection event has not yet reached us due to the 3,800-year light travel time. So when we observe this arc today, we see material ejected around 4,400 years ago from the star's perspective. Other features include what astronomers call knots, compact clumps substantially denser than their surroundings. These knots range from 0.1 to several arcseconds across, corresponding to tens to hundreds of astronomical units in linear size. Some knots show organized internal structure with apparent shells or concentric layers, suggesting they formed through discrete ejection events rather than continuous wind processes. The southwestern quadrant of the nebula displays particularly complex structure, including multiple overlapping arcs and a prominent dusty knot catalogued as VY Canis Majoris SW. This knot contains enough dust to completely obscure background starlight, appearing as a dark patch against the fainter nebular glow. The knot's properties suggest it formed when a massive blob of material was ejected from the star and subsequently cooled, allowing dust grains to condense from the gas. The chemical composition of the nebular material has been studied through spectroscopy. When atoms in the gas are excited by stellar ultraviolet radiation, they emit characteristic spectral lines that reveal elemental abundances. These studies show that VY Canis Majoris' nebula is enriched in certain elements compared to typical interstellar material. Specifically, the nebula shows elevated abundances of elements produced by nuclear fusion in massive stars. Nitrogen abundances are enhanced, indicating material processed through the CNO cycle, where carbon, nitrogen, and oxygen serve as catalysts for hydrogen fusion. Oxygen and carbon also appear at levels suggesting internal processing and convective dredge-up of fusion products. This chemical signature confirms that the nebular material originated deep within VY Canis Majoris, where nuclear reactions operate. Through convection, this processed material was transported from the interior to the surface and subsequently ejected into space. The ejection process enriches the interstellar medium with heavy elements that will eventually be incorporated into future generations of stars and planets. The dust component of the nebula has been extensively studied through infrared observations. Dust forms when gas expelled from the star cools sufficiently for atoms to condense into solid particles. In oxygen-rich environments like VY Canis Majoris, silicate dust dominates, composed primarily of silicon and oxygen compounds, along with other elements including magnesium, iron, and aluminum. These microscopic silicate grains absorb ultraviolet and visible photons from the stellar surface and re-radiate the energy at infrared wavelengths. The resulting infrared excess makes VY Canis Majoris exceptionally bright in infrared, despite appearing relatively faint in visible light. At certain infrared wavelengths, VY Canis Majoris ranks among the brightest infrared sources in the entire sky. The dust grain size distribution peaks at sub-micron dimensions, particles roughly 0.1 to 1 micrometer across. These sizes are comparable to visible light wavelengths, which explains why the dust efficiently scatters and absorbs visible radiation while remaining more transparent to longer wavelength infrared. The dust distribution is highly non-uniform throughout the nebula, concentrated in some regions, nearly absent in others, creating the complex patterns of brightness and darkness seen in images. Radiation pressure from the star's intense luminosity accelerates dust grains outward. Each photon absorbed or scattered by a dust grain transfers momentum. For grains in the size range found around VY Canis Majoris, radiation pressure can overcome gravitational attraction, driving dust outward at tens of kilometers per second. The accelerating dust drags gas along through collisions, creating a stellar wind. This dust-driven wind mechanism represents the primary mass loss process in cool supergiants and hypergiants. Cool temperatures in extended stellar atmospheres allow dust condensation at distances of a few stellar radii. Once formed, radiation pressure accelerates dust and entrained gas outward, sustaining continuous mass outflow. But the organized structures in VY Canis Majoris' nebula suggest additional mass loss mechanisms operate beyond simple dust-driven winds. Discrete arcs and knots indicate episodic ejection events that expel substantial amounts of material in relatively short bursts. These episodes might be triggered by internal instabilities related to pulsation or convective activity. Red supergiants pulsate semi-regularly with periods ranging from hundreds to thousands of days. These pulsations represent expansion and contraction of the stellar envelope, as various instabilities drive oscillations. During maximum expansion, material in the outer atmosphere can reach velocities sufficient to escape gravitational binding, especially when radiation pressure on newly formed dust provides additional outward force. Large-scale convection cells, vastly more extreme than the granulation visible on the Sun's surface, might transport material from deep within the star to the surface. These convection cells in a star like VY Canis Majoris span distances comparable to Earth's orbit or larger. When hot material rises to the surface in these giant convective currents, it can create bright, hot regions that radiate more intensely than surrounding areas. This enhanced radiation might drive localized mass loss, creating the asymmetric features observed. Magnetic fields might also shape mass outflow, though magnetic properties of extreme red supergiants remain poorly constrained. If VY Canis Majoris possesses large-scale magnetic fields, these could channel and direct mass loss along field lines, creating directional features. The bottom line is that VY Canis Majoris exhibits mass loss so extreme it exceeds the regime where theoretical models have been thoroughly validated. The star serves as an astrophysical laboratory, revealing processes operating only under the most extreme conditions that challenge our understanding of stellar structure. This extreme mass loss has profound implications for the star's fate and for understanding how large stars can actually grow. The most obvious implication concerns how much mass the star currently retains. If VY Canis Majoris formed with an initial mass typical for stars that become red supergiants, perhaps 25 to 40 solar masses, and has since lost several solar masses through winds and eruptions, its present-day mass must be substantially less than its birth mass. Current mass estimates for VY Canis Majoris, based on dynamical studies and comparison with evolutionary models, suggest the star currently contains approximately 17 to 25 solar masses. The uncertainty overlaps with, but is distinct from uncertainty in initial mass. Different evolutionary tracks produce different present masses for stars of given initial mass, depending on how much mass loss occurs and when. The fact that VY Canis Majoris currently retains only 17 to 25 solar masses, while displaying dimensions that would reach near Saturn's orbit, reveals something profound about stellar evolution. This star has become extraordinarily extended, not because it is especially massive by stellar standards, but because of its evolutionary state and internal structure. Stars achieve extreme dimensions during the red supergiant phase through internal structural changes rather than high mass alone. The core contracts as nuclear fuel, depletes, heating and driving increasingly energetic shell burning around the inert core. This shell burning releases enormous energy that must be transported outward through the envelope. The envelope responds by expanding to enormous sizes, reaching a new equilibrium between energy generation in shells and energy radiation from the surface. Expansion continues until the star either stabilizes, evolves to different temperatures and sizes, or begins losing mass so rapidly that the envelope cannot be sustained. VY Canis Majoris appears to be in this latter regime, where mass loss is so extreme the star cannot maintain equilibrium. The envelope is literally evaporating as the star struggles to radiate the energy generated in its interior. This brings us to fundamental questions about VY Canis Majoris' nature. How long can such an extreme state persist? Is this a brief phase lasting only thousands of years, or can stars maintain these conditions longer? What determines when the star finally undergoes catastrophic collapse and explodes as a supernova? Before addressing those questions, we need to understand what makes VY Canis Majoris different from typical red supergiants. The star is not merely a large example of a common type. Instead, it belongs to an even rarer category called hypergiants, objects occupying the extreme upper boundary of stellar evolution. The Hertzsprung-Russell diagram, developed independently around 1910 by Einar Hertzsprung and Henry Norris Russell, organizes stars according to temperature and luminosity. When thousands of stars are plotted on this diagram, clear patterns emerge revealing underlying physics of stellar structure and evolution. Most stars, roughly 90%, cluster along a band called the main sequence. These stars fuse hydrogen in their cores and maintain relatively stable properties over millions to billions of years depending on mass. Our Sun sits on the main sequence. So does Sirius. So do most naked-eye stars visible from Earth. Some stars lie far from the main sequence, occupying regions indicating extreme luminosity. These are supergiants, stars shining thousands to hundreds of thousands of times brighter than the Sun. The term encompasses objects at different temperatures, from hot blue supergiants like Rigel to cool red supergiants like Betelgeuse. Among supergiants, a select few shine with such extreme luminosity that astronomers classify them separately as hypergiants. These are stars with luminosities exceeding roughly 300,000 solar luminosities, placing them at the absolute ceiling of stellar brightness. VY Canis Majoris qualifies as a red hypergiant, combining extreme luminosity with the coolest surface temperatures. Hypergiant classification reflects both present evolutionary state and implied initial mass. Stars do not become hypergiants unless they formed with masses approaching the upper limit of stellar formation, perhaps 25 to 40 or more solar masses. Much of this initial mass may have been lost through winds by the time the star reaches the hypergiant phase. The term hypergiant was not formally adopted until late 20th century as observational evidence accumulated, showing certain stars had properties even more extreme than typical supergiants. Classification remains somewhat informal, with different researchers sometimes applying slightly different criteria, but general consensus places VY Canis Majoris firmly in the hypergiant category, based on extreme luminosity and spectroscopic characteristics. What makes hypergiants physically distinct from supergiants? Several characteristics set these objects apart. First, hypergiants display extreme mass loss exceeding typical supergiant wind rates by factors of 10 or more. We have already explored VY Canis Majoris' mass loss in detail. This is not unusual for hypergiants. Other confirmed hypergiants show similarly extreme wind properties. Rho Cassiopeiae, a yellow hypergiant, undergoes periodic outbursts ejecting significant fractions of a solar mass in single events lasting months. Mu Cephei, also called Herschel's garnet star, shows variable mass loss creating extensive circumstellar structure. P Cygni, the prototype of a particular spectral line profile indicating strong outflowing winds, displays mass loss signatures in its spectrum that have made it famous among stellar spectroscopists. Second, hypergiants occupy a region of the Hertzsprung-Russell diagram where theoretical models predict instability. Stars with the extreme luminosities characteristic of hypergiants generate radiation pressure approaching the Eddington limit, the point where outward radiation force balances inward gravitational force. The Eddington luminosity depends on stellar mass and composition. For a 20 solar mass star, the Eddington limit corresponds to roughly 2.5 million solar luminosities. VY Canis Majoris, shining at 270,000 to 400,000 solar luminosities, approaches but does not quite reach the Eddington limit for plausible masses. However, radiation pressure affects different atmospheric regions differently depending on how efficiently that region absorbs radiation. Dust grains absorb radiation far more efficiently than gas, meaning radiation pressure on dust-laden regions can drive mass loss even when total luminosity remains below the electron-scattering Eddington limit. This dust-assisted mass loss might allow hypergiants to shed mass at rates impossible for cleaner atmospheres. Third, hypergiants show evidence of unusual pulsational and convective activity, suggesting interiors far from equilibrium. The star's core burns helium or more advanced fuels, releasing energy at rates the envelope struggles to radiate efficiently. Mismatches between energy generation and transport create instabilities manifesting as pulsations, eruptions, and violent mass loss. Fourth, hypergiants exist in extremely brief evolutionary phases. While main sequence stars like the Sun spend billions of years in stable configurations, hypergiants persist perhaps only a few 100,000 years before evolving to different states or exploding. This brief duration makes hypergiants extraordinarily rare. Known red hypergiants in our galaxy number perhaps 10 to 20 objects depending on exact classification criteria. These include VY Canis Majoris, MU Cephei, VX Sagittarii, KY Cygni, RW Cephei, and several others. Each shows similar characteristics: extreme luminosity, cool surface temperatures, massive circumstellar nebulae from prodigious mass loss, and evidence of instability. This tiny population provides limited data for testing theoretical models of the most extreme stellar evolution phases. Each object becomes extraordinarily valuable for understanding processes operating only under conditions barely occurring anywhere in the universe at any given time. The evolutionary pathway leading to the hypergiant phase remains somewhat uncertain because multiple factors influence massive star evolution. Initial mass clearly matters, but metallicity, the abundance of elements heavier than helium in the star's composition, also plays significant roles. Metallicity affects opacity throughout stellar envelopes, influencing how efficiently energy transports from interior to surface. It also affects mass loss rates, because elements like carbon, nitrogen, and oxygen contribute to dust formation, and dust drives mass loss. Stars with higher metallicity experience stronger stellar winds and lose more mass over lifetimes. This increased mass loss can strip hydrogen envelopes before the star expands to red supergiant or hypergiant dimensions. Such stripped stars evolve to become Wolf-Rayet stars, hot, compact objects displaying fusion products at their surfaces. The metallicity of stars in the solar neighborhood is relatively high, the result of 12 billion years of chemical evolution enriching the interstellar medium with heavy elements from previous stellar generations. VY Canis Majoris formed from material already processed through multiple generations, giving it relatively high initial metallicity. In galaxies or regions with lower metallicity, stellar evolution might proceed differently. Lower metallicity means less efficient dust formation, potentially reducing mass loss rates and allowing stars to retain envelopes longer. This might permit even larger dimensions if extended atmospheres can be maintained without rapid mass loss. Alternatively, lower metallicity might prevent hypergiant formation entirely, with stars evolving through different channels bypassing extreme expansion. Complex interplay between initial mass, composition, mass loss, and internal structure means predicting massive stellar evolution. Outcomes remains challenging even with sophisticated computer models. What we know confidently is that VY Canis Majoris represents one of the most extreme outcomes accessible to massive stars in our galaxy's current chemical environment. The star has expanded to dimensions approaching theoretical limits while maintaining luminosity near the maximum stellar interiors can generate. It loses mass so rapidly that its lifetime in this phase must measure in at most tens of thousands of years. The star exists on a knife edge between different possible fates. It might continue gradual mass loss while slowly contracting and heating, eventually becoming a hot supergiant before exploding. It might undergo an eruption, ejecting large fractions of its envelope in single events, dramatically changing structure. Or it might collapse and explode relatively soon, within the next few 100,000 years or less. These alternatives are not merely academic, but represent fundamentally different pathways determining the star's final impact on surroundings and the remnant it leaves behind. Before exploring those end states, we need to understand nuclear processes occurring in VY Canis Majoris' core, the engines driving this cosmic titan's prodigious output. Deep within VY Canis Majoris, hidden beneath layers of atmosphere spanning hundreds of millions of kilometers, nuclear fusion releases energy at rates difficult to comprehend. Core temperatures reach tens of millions of degrees, creating environments where atomic nuclei collide with sufficient energy to overcome electromagnetic repulsion and fuse into heavier elements. The specific nuclear reactions occurring depend on evolutionary state, which remains somewhat uncertain. Stars evolve through sequences of burning phases, each characterized by fusion of progressively heavier elements. Understanding where VY Canis Majoris sits in this sequence provides insight into how much time remains before catastrophic collapse. The star exhausted core hydrogen millions of years ago during its main sequence phase when it appeared as a hot blue star rather than the cool red giant we observe today. Hydrogen core burning typically consumes roughly 10% of the star's hydrogen, converting it to helium through reactions releasing energy via Einstein's mass-energy relation. For a star with VY Canis Majoris' implied initial mass around 25 to 40 solar masses, hydrogen core burning lasts approximately 5 to 10 million years. This seems lengthy by human standards, but represents a tiny fraction of stellar lifetimes for lower mass stars. Our Sun burns hydrogen for 10 billion years. When core hydrogen exhaustion occurs, fusion ceases in central regions, and the core contracts under gravity. This contraction releases gravitational potential energy, heating both core and surrounding layers. Eventually, a shell of hydrogen just outside the helium core reaches temperatures sufficient for fusion, igniting hydrogen shell burning. Shell hydrogen burning produces luminosity exceeding core hydrogen burning. The star brightens substantially and begins expanding as outer layers respond to increased energy flow from the interior. This marks the beginning of the red giant phase for lower mass stars, or the red supergiant phase for massive stars. As the helium core contracts and heats, it eventually reaches temperatures around 100 million Kelvin, sufficient for helium fusion to ignite. Helium burning through the triple alpha process converts 3 helium nuclei into 1 carbon nucleus, releasing energy that briefly stabilizes the core. The star now burns helium in its core, while hydrogen burns in a surrounding shell. Helium core burning lasts perhaps 1 million years for a star of VY Canis Majoris' mass, roughly 1/10 the hydrogen burning duration. Nuclear fusion of helium releases less energy per unit mass than hydrogen fusion, and higher core temperatures required for helium burning increase energy loss through neutrino emission, further shortening this phase. When helium exhausts in the core, the carbon-oxygen core that remains contracts further. For sufficiently massive stars, this contraction heats the core until carbon ignites at temperatures around 500 million Kelvin. Carbon burning converts carbon into neon, magnesium, and other elements through various reactions. Increasingly high temperatures required for burning heavier elements mean successive burning stages proceed more rapidly. Carbon burning lasts perhaps 1,000 years. Neon burning takes a few years once ignited. Oxygen burning proceeds over mere months. Silicon burning, the final stage before ion accumulation, completes in days. Where does VY Canis Majoris sit in this sequence? Observational data does not directly reveal core composition because we cannot see into stellar interiors. We must infer evolutionary state from surface properties combined with theoretical models. The extreme luminosity suggests advanced burning stages. Stars brighten substantially when burning helium or heavier elements, because shell burning is inherently more luminous than core burning for stellar structure reasons. The star's cool temperature combined with extreme luminosity places it where post-main sequence stars spend most remaining lives. Most researchers believe VY Canis Majoris currently burns helium in its core, or has perhaps advanced to carbon burning. If still in helium burning, the star might persist tens or hundreds of thousands of years before advancing to rapid burning stages. If already burning carbon or beyond, remaining lifetime shrinks to thousands of years at most. Uncertainty in evolutionary state stems partly from challenges modeling the most massive stars. The extreme mass loss VY Canis Majoris exhibits affects evolution in ways standard models do not capture accurately. When stars lose mass, they lose primarily from outer hydrogen envelopes. This mass loss effectively peels away outer layers, potentially exposing interior processed material. For stars with extreme mass loss, like VY Canis Majoris, evolutionary tracks become path-dependent in ways complicating predictions. Current structure depends not only on initial mass, but also on how rapidly mass was lost and when that loss occurred. Different mass loss histories produce different present structures, even for stars with identical initial masses. Despite these uncertainties, we confidently state that VY Canis Majoris is in advanced evolutionary stages, approaching the end of nuclear burning phases. The star will not persist in current form for millions of years. Remaining lifetime measures in hundreds of thousands of years at most, possibly far less. Energy generated by nuclear burning in VY Canis Majoris' core must transport outward through hundreds of millions of kilometers of stellar material before radiating into space from the surface. This energy transport process determines stellar structure and explains why the star has expanded to such enormous dimensions. In deep interior surrounding burning regions, energy transports primarily through radiation. Photons generated by nuclear reactions diffuse outward, repeatedly absorbed and re-emitted by stellar material. Each photon random walks through the star, taking thousands or millions of years to migrate from core to surface despite traveling at light speed. But in cooler outer regions of massive evolved stars, radiation becomes less efficient at transporting energy. Steep temperature gradients between hot interior and cool surface drive convection, a process where physical gas motion carries energy more efficiently than radiation. Convective regions form when radiative temperature gradients become too steep. Hot material becomes buoyant relative to cooler surroundings and rises like hot air rising over fire. As it rises, it expands and cools, eventually becoming denser than surroundings and sinking back. This overturning circulation carries energy upward far more efficiently than radiative diffusion, where strong temperature gradients exist. In red supergiants and hypergiants like VY Canis Majoris, the convective envelope extends inward to encompass most stellar volume outside nuclear burning shells. Individual convection cells span distances measured in astronomical units, creating rising and sinking currents with velocities of tens of kilometers per second and temperatures differing by thousands of degrees between rising and sinking material. This convection has observable consequences. Surfaces of nearby red supergiants, like Betelgeuse, have been imaged with sufficient resolution to reveal bright and dark patches corresponding to convective cells. These patches appear roughly uniform in size, with dimensions comparable to Earth's orbital radius. They change configuration over months to years as convective patterns evolve. VY Canis Majoris almost certainly displays similar surface structure on even grander scales, though the distance prevents direct imaging with current technology. The star's variability and the asymmetric mass loss patterns likely connect to surface convection driving local brightness, and mass loss rate variations. The energy transported by this convection originates from shell burning surrounding the core. In VY Canis Majoris' current state, helium shell burning and possibly hydrogen shell burning release energy that flows outward through the convective envelope. The envelope structure adjusts to transport this energy efficiently while radiating it away from the cool extended surface. The cool surface temperature, around 3,200 Kelvin, allows molecules to exist in the outer atmosphere. Spectroscopy detects titanium oxide, water vapor, carbon monoxide, and other molecules whose presence would be impossible in hotter stars. These molecules affect how light escapes, creating absorption features that allow astronomers to measure stellar properties. The density at the photosphere defies terrestrial intuition. While the core remains far denser than any Earth material, with densities approaching those in atomic nuclei in innermost regions, outer layers expand to extraordinarily low densities. At the visible surface, densities drop to roughly 1/1000th of Earth's atmospheric density at sea level. The outer atmosphere qualifies as better vacuum than most laboratory equipment can achieve. High vacuum chambers used for scientific experiments typically achieve densities millions of times higher than VY Canis Majoris' photospheric density. Yet this incredibly tenuous material produces the light we observe. Photons generated in deeper, denser regions scatter and absorb through this extended atmosphere before escaping into space. The long path through tenuous material allows even weak absorption processes to affect emerging radiation significantly. The characteristic red color comes not from thermal radiation alone, but from complex absorption by molecules and atoms in cool outer layers. This produces the deep red hue visible through telescopes, quite different from the blue-white glare of hot main sequence stars or the yellow-white appearance of sun-like stars. The pulsation of VY Canis Majoris adds another layer to understanding its structure. The star does not maintain constant size, but oscillates over periods around 1,000 to 2,000 days, roughly 3 to 5 years. The star breathes in and out like a cosmic lung, expanding and contracting with semi-regular periodicity. Pulsation mechanisms relate to how opacity changes with temperature in outer layers. Opacity describes how effectively material blocks radiation. As the star compresses, it heats slightly, changing how effectively material absorbs radiation. In certain temperature ranges, compression increases opacity, trapping radiation, increasing pressure, driving expansion. Expansion leads to cooling, decreasing opacity, allowing radiation escape, decreasing pressure, allowing contraction to begin again. This opacity-driven instability creates regular pulsations. For VY Canis Majoris, pulsation periods spanning years reflect the star's enormous dimensions and low density. During maximum expansion, the star might exceed 1,600 solar radii. During minimum, it might contract below 1,300 solar radii, representing variation of 10% or more in radius, corresponding to over 30% variation in volume. Mass loss from VY Canis Majoris proceeds through multiple mechanisms operating simultaneously. Radiation pressure accelerates dust grains forming in the cool outer atmosphere. When temperatures drop below roughly 1,500 Kelvin in the extended envelope, silicate dust can condense from gas phase. These grains absorb starlight efficiently, experiencing strong radiation pressure accelerating them outward. Accelerating dust drags gas through collisions, creating stellar winds carrying material away from the star. This dust-driven wind mechanism operates continuously, steadily eroding the envelope over thousands of years. Mass loss rate depends on how much dust forms, which depends on temperature, chemistry, and dynamics in the extended atmosphere. Pulsation drives shocks through outer layers, episodically ejecting material. When the star compresses during pulsation cycles, compression propagates outward as waves. These waves steepen into shocks as they travel through decreasing density profiles. Shocks accelerate material to velocities exceeding local escape velocity, launching discrete shells into space. Convective motions can lift material to heights where it escapes gravitational binding. The enormous convection cells transport material upward to the outer atmosphere, where it finds itself in regions of weaker gravitational binding. Given extremely low surface gravity, material does not need much additional velocity to escape. Surface gravity of VY Canis Majoris is perhaps 100,000 times weaker than Earth's, making escape relatively easy for material reaching the outer atmosphere. The combined effect produces mass loss rates millions of times greater than our Sun's solar wind. The solar wind carries roughly 1 million tons per second. VY Canis Majoris probably loses the Sun's total mass every few thousand to 10,000 years. Over remaining lifetime, perhaps a few 100,000 years at most, before core collapse triggers supernova, it will shed several solar masses into surrounding space. Material leaving today travels outward at roughly 10 to 30 kilometers per second. This ejected material creates circumstellar structures, providing evidence of recent evolutionary history. Shells of previously ejected material surround VY Canis Majoris at various distances, glowing faintly in infrared as dust grains absorb stellar radiation and re-emit at longer wavelengths. Each shell represents a particular mass loss epoch, frozen at the distance reached since ejection. Episodes of enhanced mass loss appear as denser shells. Periods of reduced loss appear as gaps. The distribution encodes information about how mass loss rate varied over tens of thousands of years. Comparison with other giant stars reveals where VY Canis Majoris fits within the extreme stellar population and why astronomers recognize it as extraordinary even among supergiants. Before VY Canis Majoris gained wide recognition, and even now in certain measurements, several other red supergiants compete for size records. VY Scuti, located about 9,500 light-years away in Scutum, held the record for largest known star through much of the 2010s. Early measurements suggested dimensions approaching 1,700 solar radii. Subsequent observations revised estimates somewhat, but VY Scuti remains among the largest known stars with radius around 1,200 to 1,600 solar radii depending on analysis method. Stevenson 218, buried behind heavy dust in the Stevenson 2 cluster roughly 20,000 light-years away, represents another extreme red supergiant. Distance uncertainty and heavy extinction complicate measurements, but estimates place its radius around 2,150 solar radii, potentially larger than VY Canis Majoris though, with substantial uncertainty. WOHG 64, located in the Large Magellanic Cloud about 160,000 light-years away, displays an extensive dusty torus or disk surrounding the star. The stellar radius measures perhaps 1,500 to 1,600 solar radii, smaller than VY Canis Majoris's main body, but the dust structure extends much farther. What distinguishes VY Canis Majoris from these competitors? Primarily the convergence of multiple measurement techniques producing consistent results, placing this star among the absolute largest, combined with its relative proximity, allowing detailed study. Distance to VY Canis Majoris, while uncertain by 20 to 30%, is better constrained than for more distant competitors like Stevenson 2-18. The star is bright enough for high-quality spectroscopy and interferometry. The nebula is close enough for resolved imaging showing detailed structures. This combination makes VY Canis Majoris arguably the best-studied extreme red supergiant, even if it might not hold the absolute size record. The density contrast within VY Canis Majoris captures this fundamental strangeness. Objects larger than Saturn's orbit somehow weigh less per unit volume than the air you breathe when averaged across their entire extent. This seeming impossibility arises from how stellar structure distributes mass. The dense core containing nuclear-burning regions occupies tiny fractions of total volume. The vast extended envelope defining the visible star contains relatively little mass spread incredibly thin. Consider the average density comparison directly. VY Canis Majoris contains perhaps 17 to 25 solar masses, depending on how much material mass loss removed. This mass occupies a volume roughly 7 to 10 billion times larger than the Sun. Average density therefore falls roughly 7 to 10 billion times below the Sun's average density. Our Sun has average density approximately 1.4 grams per cubic centimeter, slightly denser than water. Dividing by 7 to 10 billion gives average density for VY Canis Majoris around 1 to 2 times 10 to the power of minus 10 grams per cubic centimeter. This is far less dense than Earth's best laboratory vacuums. Earth's atmosphere at sea level has density about 0.001 grams per cubic centimeter. Average density inside VY Canis Majoris falls roughly 10 million times lower than sea level air. A cubic meter of material from the average region would contain less matter than a cubic meter of interplanetary space in our solar system. Of course, this average obscures enormous variation. The core remains extremely dense, with central regions approaching nuclear densities where matter behaves according to quantum mechanical rules, quite different from ordinary materials. But the outer atmosphere where we measure the star's boundary is essentially empty space by any practical definition. This density structure creates the vast dimensions making VY Canis Majoris a record holder. The relatively modest total mass spreads across such enormous volume that average density plummets to nearly nothing. The star maintains this extended configuration through continuous energy flow from nuclear burning regions, supporting the tenuous envelope against gravitational collapse. The physics allowing such extreme dimensions relates to how gravitational binding energy compares to thermal energy at different radii. In outer layers, thermal energy only marginally exceeds gravitational binding energy. Escape velocity from VY Canis Majoris' surface is perhaps 20 to 30 kilometers per second, compared to over 600 kilometers per second from our Sun's surface. The star maintains its enormous envelope through continuous adjustments rather than stable equilibrium. Energy flows outward from burning shells, heating the envelope and preventing collapse. Mass flows outward through stellar winds, gradually reducing envelope mass. Pulsation drives oscillations moving material back and forth, occasionally ejecting portions into space. The system exists in dynamic quasi-equilibrium, constantly adjusting but maintaining overall structure over timescales of thousands of years. This is not a stable configuration like our Sun's, but a temporary state in a star's death throes. Despite these challenges, the basic picture of how VY Canis Majoris reached its current state seems well established in broad outlines. A massive star formed roughly 8 to 10 million years ago when a molecular cloud collapsed under gravity. The star burned through hydrogen in its core over 5 to 10 million years, while appearing as a hot blue star. Shell burning triggered expansion into a red supergiant phase, lasting perhaps 100,000 years or less. The star continues evolving toward inevitable supernova explosion, while we observe it during this fleeting moment of maximum extension. What remains certain is the remarkable nature of this object. VY Canis Majoris represents stellar evolution pushed to extremes. The same physics governing our modest Sun produces, under different initial conditions, an object so vast that comprehending its true nature requires abandoning all terrestrial intuitions about size, density, and structure. Every red supergiant is a dying star. The bloated dimensions and cool red surface defining this stellar class represent symptoms of impending catastrophe, not stable characteristics of healthy stellar objects. Deep within VY Canis Majoris, nuclear processes race toward an inevitable endpoint that will transform this cosmic giant into something utterly different. The death of VY Canis Majoris will produce one of the most violent events possible in our universe. The timeline ticks relentlessly forward with each passing second. Somewhere in the core, nuclear fusion converts increasingly heavy elements at rates measured in years, months, or days, rather than the millions of years characterizing earlier burning phases. Or perhaps those final stages have not yet begun and the star still burns through oxygen or neon. Or perhaps silicon burning has already completed and the core is collapsing at this very moment, though the signal has not yet reached the surface, let alone traveled the 3,800 light-years to Earth. We cannot know the precise evolutionary state because looking into stellar cores requires detecting particles traveling at nearly light speed, and even those particles take years to reach us from this distant star. The information we receive today tells us about conditions 3,800 years ago. The star's current status remains forever hidden behind the finite speed of light. What we know with confidence is that core collapse supernovae follow predictable physics once the iron core grows sufficiently massive. Iron represents the endpoint of stellar nucleosynthesis for a fundamental reason rooted in nuclear physics. Every element lighter than iron releases energy when fused into heavier elements. This energy release powers stars through entire lives, from hydrogen burning on the main sequence through helium, carbon, neon, oxygen, and silicon burning in evolved massive stars. Iron sits at the peak of the nuclear binding energy curve. Iron 56, the most common isotope, has the highest binding energy per nucleon of any element. Fusing iron into heavier elements does not release energy, but requires energy input. The star cannot generate power by fusing iron. The iron core is nuclear ash, final waste product of stellar fusion, incapable of providing energy needed to support against gravity. Every gram of iron accumulating in the core represents material that will never again contribute to holding up the star. The core grows heavier while contributing nothing to the star's energy budget. Silicon burning deposits fresh iron into the core at prodigious rates during the final days of a massive star's life. Silicon burning phase lasts roughly 1 to 2 days, converting silicon-rich shells surrounding the core into iron group elements. Each day adds roughly 1/10 of a solar mass to the iron core. The core grows like a tumor, absorbing energy rather than producing it. When iron mass exceeds roughly 1.4 solar masses, a threshold called the Chandrasekhar limit, after physicist Subrahmanyan Chandrasekhar who calculated it, electron degeneracy pressure can no longer support the core against gravitational collapse. This limit represents a fundamental boundary where quantum mechanical effects normally preventing matter from compressing indefinitely finally fail against overwhelming gravitational force. Electron degeneracy pressure arises from the Pauli exclusion principle, forbidding 2 electrons from occupying the same quantum state. In normal matter, this restriction limits how tightly electrons can pack together. But above the Chandrasekhar limit, gravity becomes strong enough to force electrons and protons together, converting them into neutrons and removing the electrons providing degeneracy pressure. Support vanishes catastrophically. What happens next unfolds with terrifying speed, compressing events that would normally require astronomical timescales into fractions of a second. The core implodes. Material falls inward at roughly 1/4 light speed, approximately 75,000 kilometers per second. Density increases by factors of trillions within less than a second, as the core compresses from roughly Earth-sized dimensions to a sphere perhaps 20 kilometers across. To grasp this compression, imagine squeezing Earth to the size of a small city. All mass remains, but volume decreases by factors approaching 1 billion. Density in the collapsing core approaches and exceeds the density of atomic nuclei, roughly 200 trillion grams per cubic centimeter. A teaspoon of this material would weigh hundreds of millions of tons. During collapse, protons and electrons merge, forming neutrons through electron capture or inverse beta decay. Each reaction produces a neutrino, a nearly massless particle interacting so weakly with matter, it typically passes through entire planets without stopping. The collapsing core releases enormous quantities of these ghostly particles, roughly 10 to the power of 58 individual neutrinos within seconds. These neutrinos carry away gravitational binding energy released during collapse, more energy than the star radiated as light throughout its entire 8 to 10 million year lifetime combined. The neutrino luminosity during core collapse exceeds the combined light output of every star in the observable universe for a brief moment. Yet these particles are so weakly interacting that most pass through the surrounding stellar envelope without depositing any energy. For VY Canis Majoris, the collapsing core probably contains between 1.5 and 2.5 solar masses, depending on how much mass the star lost through winds over its red supergiant lifetime. The initial implosion compresses this material from roughly Earth-sized dimensions to a sphere perhaps 12 to 15 kilometers across within about 1 second. Densities approach those found in atomic nuclei where individual neutrons and protons touch directly. The strong nuclear force, operating only at these incredibly short ranges, suddenly becomes relevant on macroscopic scales. Nuclear matter has fundamental incompressibility. You cannot squeeze neutrons together beyond a certain point because the strong force becomes repulsive at extremely short distances. This repulsion halts collapse suddenly, like dropping a rubber ball onto concrete. The infalling material bounces off the newly formed neutron star core, creating an outward-moving shock wave. The bounce converts kinetic energy of infall into kinetic energy of outward expansion. This bounce shock carries enormous energy, roughly 10 to the power of 51 ergs, or about 1% of total gravitational energy released. But the shock does not simply blast through the star, creating the observable supernova. Instead, it stalls. Overlying stellar layers absorb the shock's energy through nuclear dissociation, breaking apart heavy nuclei into constituent protons and neutrons. Each iron nucleus the shock encounters requires energy to disassemble, robbing the shock of momentum. Within roughly 100 milliseconds, the shock stalls at a radius perhaps 100 to 200 kilometers, far short of the stellar surface. For decades, astronomers and physicists puzzled over how supernovae actually explode given this shock stalling problem. Computer simulations repeatedly showed bounce shocks dying before reaching surfaces, leaving stars to collapse entirely into black holes without visible explosions. Observed supernovae clearly required some mechanism to revive stalled shocks. The answer involves those neutrinos released during neutron formation. Although neutrinos interact very weakly, densities in regions behind stalled shocks are so extreme that even weakly interacting particles deposit significant energy. Perhaps 1% of outgoing neutrino flux gets absorbed in layers just outside the nascent neutron star, heating material and providing energy needed to revive shocks. This neutrino heating mechanism remains active research with many details uncertain. Three-dimensional simulations suggest turbulent convection and hydrodynamic instabilities play crucial roles, helping channel neutrino energy into shock revival. Explosion mechanisms appear far more complex than simple spherical models suggested, involving asymmetric flows and chaotic dynamics. Once revived, shock waves resume outward journeys through stellar envelopes. For compact stars like blue supergiants, this journey requires only hours. For enormously extended red supergiants like VY Canis Majoris, shocks must traverse nearly 2 billion kilometers of tenuous stellar material. Even traveling at thousands of kilometers per second, this journey requires many hours. During this journey through envelopes, nuclear reactions in shock-heated material synthesize heavy elements that cannot be made through normal stellar fusion. Extreme temperatures and densities behind shocks enable rapid neutron capture processes building elements heavier than iron. Gold, platinum, uranium, thorium, and dozens of other heavy elements form in extreme conditions behind shock fronts. This nucleosynthesis contributes to galactic chemical evolution. Heavy elements ejected by supernovae mix with the interstellar medium and eventually become incorporated into new stellar and planetary generations. Every gold atom in jewelry, every uranium atom in nuclear reactors, every platinum atom in catalytic converters was synthesized in a supernova explosion and distributed across space by the resulting debris cloud. When shocks finally break through surfaces, supernovae become visible to external observers. This shock breakout produces brilliant flashes as shock waves suddenly encounter tenuous outer atmospheres and accelerate material to extreme velocities. Stars brighten by factors of billions within hours, releasing radiation across entire electromagnetic spectra from radio through gamma rays. Shock breakout from red supergiants differs dramatically from breakout in more compact progenitors. Extended diffuse atmospheres produce relatively gradual brightening as shocks propagate through outer layers. This contrasts with sharp, bright ultraviolet flashes expected from blue supergiant explosions where shocks encounter denser material at stellar surfaces. Peak luminosity of supernovae from red supergiants like VY Canis Majoris typically reaches several billion solar luminosities. For periods of days to weeks, single exploding stars outshine every other star in host galaxies combined. The Milky Way contains perhaps 400 billion stars, yet one dying red supergiant can temporarily produce more light than all of them together. From Earth 3,800 light-years away, the supernova might briefly become visible to the naked eye, perhaps reaching magnitude 2 or 3, comparable to moderately bright stars in the Big Dipper. Despite intervening dust currently hiding the star from optical observation, explosion energy will heat surrounding dust, which will re-radiate at infrared wavelengths. This infrared brightening might appear more prominent than optical emission due to heavy extinction along the line of sight. The explosion will be classified as Type II supernova based on presence of hydrogen lines in its spectrum. Extended hydrogen-rich envelopes ensure hydrogen dominates outer ejecta, producing characteristic spectral signatures distinguishing these explosions from Type I supernova occurring in stars that lost hydrogen envelopes. For VY Canis Majoris, explosion energy will likely exceed 10 to the power of 44 joules, a unit astronomers call 1 Beth, after physicist Hans Bethe, who contributed foundational work on stellar nucleosynthesis and supernova physics. This energy, released in seconds during core collapse but distributed to visible explosion over hours, roughly equals 1% of total energy our Sun will radiate over its entire 10 billion year lifetime. Yet even this staggering output represents only about 1% of total energy released during core collapse. Remaining 99% escapes as neutrinos, invisible to most detectors, but potentially detectable by specialized facilities on Earth, if operating and properly oriented. When supernova 1987, A exploded in the Large Magellanic Cloud, roughly 168,000 light-years away, detectors worldwide registered a total of 25 neutrinos. 12 were captured by Kamiokande 2 in Japan, 8 by IMB detector in the United States, 5 by Baksan detector in the Soviet Union. That detection, involving just a handful of particles from an extragalactic explosion, confirmed theoretical predictions about neutrino production in collapsing cores. and earned a share of the 2002 Nobel Prize in Physics. For a galactic supernova like VY Canis Majoris will eventually produce, modern detectors would register thousands or tens of thousands of neutrino events over roughly 10 seconds. Super Cameo Candor detector in Japan, Ice Cube detector at the South Pole, and other neutrino observatories worldwide would all record this flood. Resulting data would provide unprecedented information about core collapse physics, including details about neutron star formation, explosion mechanism, and neutrino properties. The neutrino signal would arrive at Earth several hours before any electromagnetic radiation, because neutrinos escape cores immediately, while light must wait for shocks to reach surfaces. This advanced warning would allow astronomers to point telescopes towards supernovae before visible brightening begins, capturing crucial early phases normally missed. The Supernova Early Warning System, an international network of neutrino detectors, exists specifically to provide this advanced notification. When multiple detectors register neutrino bursts consistent with galactic supernovae, alerts are distributed to observatories worldwide within minutes, allowing rapid response. Material ejected by supernovae expands outward at velocities reaching 10,000 kilometers per second or more in fastest moving layers. For comparison, Space Shuttle orbited Earth at roughly 8 kilometers per second. Supernova ejector moves more than 1,000 times faster than any spacecraft humans have built. For stars as large as VY Canis Majoris, ejector mass might reach 10 to 15 solar masses, depending on how much material the progenitor retained in envelopes prior to explosion. This material includes hydrogen and helium layers, forming the extended red supergiant atmosphere, products of nuclear burning in various shells, and heavy elements synthesized during explosions. Expanding debris sweeps through surrounding space at velocities ensuring it remains distinct from ambient interstellar medium for thousands of years. Sharp boundaries between fast-moving ejector and stationary surroundings create shock waves heating material to temperatures of millions of degrees, producing X-ray emission detectable across vast distances. The enriched material from massive star supernovae provides heavy elements necessary for rocky planets and biological chemistry. Every oxygen atom you breathe was synthesized in a massive star through helium and carbon burning. Every calcium atom in your bones, every phosphorus atom in your DNA, every copper atom in your neurons traces back to stellar nucleosynthesis and supernova distribution. The death of VY Canis Majoris will seed surrounding space with raw materials for future solar systems. In perhaps 1 billion years, material ejected by this explosion will have mixed with the interstellar medium and become incorporated into new molecular clouds. Those clouds will collapse, forming new stars, some with planetary systems where heavy elements from VY Canis Majoris become components of rocks, oceans, atmospheres, and perhaps even living organisms. This cosmic recycling connects us directly to stellar death. The carbon in your body, the oxygen in your lungs, the iron in your blood all passed through stars that exploded before our solar system formed. You are made of stellar debris. The atoms comprising your body have histories spanning billions of years, processed through multiple stellar generations before assembling into the form you currently inhabit. The expanding supernova remnant will initially glow brightly as shock-heated material radiates energy through various physical processes. Free electrons spiraling in magnetic fields produce synchrotron radiation, visible at radio wavelengths. Hot gas emits thermal X-rays as electrons collide with ions. Optical emission comes from specific atomic transitions as gas cools and recombines over decades and centuries. The remnant will become visible as an expanding shell of gas similar to the Crab Nebula or Cassiopeia A that we observe from historical supernovae in our galaxy. The Crab Nebula resulted from a supernova observed by Chinese astronomers in the year 1054 CE. Nearly 1,000 years later, This remnant still spans roughly 11 light-years across and continues expanding at roughly 1,500 kilometers per second. Future astronomers with sufficiently powerful telescopes will watch debris clouds from VY Canis Majoris grow over centuries, mapping distributions of ejected material and searching for clues about explosion mechanisms. Asymmetries and structures in remnants preserve information about chaotic processes occurring during explosions. At centers of expanding debris will sit stellar remnants, compressed cores left behind after explosions blast away outer layers. The exact nature depends on mass remaining in collapsed cores after explosions, which in turn depends on complex dynamics. Simulations struggle to predict precisely. If remnant mass falls below roughly 2 to 3 solar masses, neutron stars will form. Neutron stars represent matter compressed to nuclear densities, supported against further collapse by neutron degeneracy pressure and repulsive components of strong nuclear force. These objects pack more mass than our Sun into spheres roughly 20 kilometers across, creating surface gravities billions of times stronger than Earth's. If neutron stars form from VY Canis Majoris, they will be born spinning rapidly due to conservation of angular momentum during core collapse. Original massive stars rotate slowly, perhaps once every few months. When cores collapse by factors of roughly 100,000 in radius, conservation of angular momentum increases rotation rates by factors squared. Resulting neutron stars might spin tens or hundreds of times per second initially. Young neutron stars also possess intense magnetic fields, typically 1 trillion times stronger than Earth's. These fields form during core collapse through flux compression, as magnetic fields of original stars get squeezed into much smaller volumes. Combination of rapid rotation and strong magnetic fields makes young neutron stars potentially observable as pulsars. Pulsars emit beams of radio waves along magnetic axes generally not aligned with rotation axes. As neutron stars spin, these beams sweep across the sky like lighthouse beams. If Earth happens to lie in beam paths, we detect regular pulses of radio emission, with periods matching neutron star rotations. The pulsar at the center of the Crab Nebula formed in the 1054 supernova still pulses 30 times per second, nearly 1,000 years later. It has slowed from its original rotation rate due to energy losses from magnetic braking, but it remains one of the most energetic pulsars known. A neutron star from VY Canis Majoris would likely show similar behavior, potentially detectable as a new pulsar within expanding debris clouds. If remnant mass exceeds roughly 2 to 3 solar masses, not even neutron degeneracy pressure can support against further collapse. Cores will continue compressing until forming black holes, objects so dense that not even light can escape gravitational pulls. For VY Canis Majoris, outcomes remain genuinely uncertain. Initial stellar mass suggested 25 to 40 solar masses. Mass loss through winds during red supergiant phases removed significant material, perhaps reducing current mass to 17 to 25 solar masses. The fraction remaining in collapsed cores depends on explosion dynamics and mass ejection that simulations struggle to predict precisely. Boundaries between neutron star and black hole formation depend not only on core mass, but also on equations of state of nuclear matter at extreme densities. These equations remain incompletely understood, introducing uncertainty into predictions about remnant outcomes, even when progenitor properties are known. If black holes form instead of neutron stars, they will be initially invisible, except through gravitational effects on surrounding material. Unlike neutron stars, black holes do not emit radiation directly. Any light or radio waves detected comes from material falling into black holes, not from black holes themselves. Gas from supernova ejector that fails to escape vicinity will fall back towards central remnants. If this material possesses sufficient angular momentum, it will form accretion disks around black holes. Friction within disks heats gas to extreme temperatures, producing X-ray emission detectable by orbiting observatories. Black hole mass might reach 5 to 10 solar masses, making it comparable to black holes detected through gravitational wave observations by LIGO and Virgo. Gravitational wave signals from core collapse represent active research distinct from well-understood signals produced by compact object mergers. Unlike clean chirp signals from merging black holes or neutron stars, core collapse produces more complex stochastic gravitational wave emission, reflecting turbulent asymmetric explosion dynamics. Detectors like LIGO, Virgo, and CAGRA might detect gravitational waves from galactic supernovae, providing information about core dynamics completely inaccessible through electromagnetic observations. Gravitational waves originate from collapsing cores during crucial seconds when explosions develop, revealing processes hidden beneath stellar envelopes. The shock waves will propagate through the stellar cluster environment, potentially affecting nearby stars' evolution. The timeline for VY Canis Majoris' specific demise remains frustratingly uncertain. Despite understanding the physics involved, red supergiants can persist for hundreds of thousands of years before core collapse, depending on initial mass and mass loss history. Most massive evolve more quickly through advanced burning stages, potentially collapsing within tens of thousands of years after becoming red supergiants. Less massive stars might persist much longer. Observational indicators potentially revealing imminence of core collapse remain subjects of active research. Some theorists suggest final burning stages should produce detectable changes in stellar properties, perhaps unusual variability, enhanced mass loss, or subtle spectral changes reflecting changing interior conditions. But predictions remain uncertain and have not been confirmed observationally. The red supergiant Betelgeuse in constellation Orion underwent dramatic dimming events in late 2019 and early 2020, sparking widespread speculation about imminent supernova. The normally brilliant star faded to roughly 1/3 typical brightness, prompting headlines asking whether we were about to witness stellar explosion in real time. Subsequent analysis attributed dimming to large dust clouds ejected by the star passing through our line of sight, combined with coincidental surface cooling during regular pulsation cycles. Betelgeuse was not dying, merely sneezing. The star has since returned to normal brightness and will likely persist for another 100,000 years before exploding. The event demonstrated both public fascination with supernova predictions and difficulty making such predictions reliably. For VY Canis Majoris, enormous distance and heavy dust obscuration prevent detailed monitoring possible for closer stars. We cannot track subtle brightness variations signaling changing interior conditions. We cannot obtain high-resolution spectra revealing compositional changes in stellar winds. We cannot image stellar surfaces looking for unusual convective patterns or mass ejection events. The supernova, when it occurs, will likely surprise astronomers on Earth. First indication might be floods of neutrinos registered by detectors worldwide, arriving several hours before any electromagnetic brightening. Alternatively, we might detect supernovae through infrared brightening as explosions heat surrounding dust, or through gravitational waves if detectors operate at sufficient sensitivity. The light from that supernova has perhaps already begun its 3,800-year journey toward Earth. The core of VY Canis Majoris might have collapsed thousands of years ago, with resulting explosions expanding outward through stellar envelopes, breaking through surfaces, and sending photons racing toward distant observers. Those photons would currently be traveling through interstellar space, approaching our positions at light speed, carrying news of events occurring before earliest human civilizations developed writing. Alternatively, core collapse might lie hundreds of thousands of years in the future, with stars continuing to burn through remaining nuclear fuel in sequences of increasingly rapid stages characterizing final evolution of massive stars. The present-day status of VY Canis Majoris remains forever uncertain, hidden behind finite light speed, limiting our access to simultaneous information about distant cosmic events. What remains certain is that this star will die violently. Physics governing massive stellar evolution permits no other outcome. The iron core will grow until exceeding the Chandrasekhar limit and collapsing. Collapse will trigger neutron star or black hole formation. Gravitational energy released will drive explosions blasting away stellar envelopes. Explosions will scatter enriched material across light years of space while leaving behind compact remnants. This fate awaits every red supergiant that has ever existed or will ever exist. The physics operates the same throughout the observable universe. In distant galaxies, as in our own Milky Way, massive stars burn bright and die young, their deaths enriching cosmic environments with heavy elements needed for rocky planets and complex chemistry. The death of VY Canis Majoris will be among the most spectacular events occurring in our galaxy during the next million years. It will briefly outshine hundreds of billions of ordinary stars combined. It will produce neutrinos detectable across the entire Milky Way and possibly neighboring galaxies. It will generate gravitational waves potentially registered by Earth detectors. It will create expanding debris clouds future astronomers will study for millennia, and it will mark the end of the largest known star in the observable universe, or at least among the largest, transforming a cosmic giant that could swallow our inner solar system into either a city-sized ball of neutrons or a gravitational abyss from which nothing can escape. The transformation will be complete within seconds during core collapse phases, though visible manifestations will unfold over hours to weeks. We are privileged to observe VY Canis Majoris during brief cosmic moments before this destruction occurs. Future observers will know this star only through remnants it leaves behind and debris clouds scattered across surrounding space. The largest known star will become a footnote in astronomical history, its record eventually broken by some newly discovered giant, its death commemorated in expanding shells of enriched gas persisting for millennia. VY Canis Majoris represents more than an astronomical curiosity or a record holder in cosmic catalogues. The existence of such an extreme object probes fundamental questions about how matter organizes under the most extreme conditions nature allows. The largest known stars reveal both capabilities of stellar physics to produce monstrous objects and limitations, preventing even larger stars from forming. Understanding these limits teaches us something profound about the universe. The first limitation relates to stellar birth. Stars form when gas clouds collapse under gravity, a process repeated countless trillions of times throughout cosmic history. But this collapse does not produce arbitrarily massive objects. Nature imposes boundaries constraining how large stars can grow during formation. As protostars accumulate mass from surrounding clouds, increasing luminosity generates radiation pressure pushing against infalling material. Growing stars essentially fight against further growth, their own energy output resisting gravitational attraction pulling material inward. Eventually, in the most massive forming stars, radiation pressure balances gravitational attraction and terminates further growth. This feedback limits maximum initial stellar mass to roughly 150 to 300 solar masses, depending on gas cloud metallicity and other environmental factors. Metallicity refers to abundances of elements heavier than helium, affecting how efficiently radiation couples to matter and exerts pressure. Stars more massive than this limit cannot form through normal accretion because radiation pressure prevents continued material accumulation before stars reach higher masses. Forming stars literally blow away their own food supplies. Halting growth at what seems arbitrary but actually reflects fundamental physics. The most massive stars ever observed, objects like R13601 in the Large Magellanic Cloud, weigh in at perhaps 200 to 300 solar masses. These extreme objects live extraordinarily short lives by stellar standards, burning through fuel in mere millions rather than billions of years. They represent upper boundaries of what stellar physics permits for initial stellar mass. But initial mass does not translate directly into final size. This distinction proves crucial for understanding why VY Canis Majoris holds its record. The most massive stars are not the largest stars. These two categories describe different extremes peaking in different mass ranges. The red supergiant phase producing the largest stellar dimensions occurs preferentially in stars with initial masses between roughly 8 and 40 solar masses. Stars more massive than this upper limit evolve differently, often losing hydrogen envelopes entirely before expanding to red supergiant proportions. Intense stellar winds driven by extreme luminosity strip away outer layers, exposing hot compact interiors. These stripped stars become Wolf-Rayet objects, compact and incredibly luminous, but relatively small in physical dimensions, typically only a few solar radii across, despite masses exceeding 20 suns. The sweet spot for maximum stellar size appears to lie in mass ranges, where stars retain hydrogen envelopes while evolving slowly enough to expand dramatically. Stars around 20 to 40 solar masses occupy this optimal range. They lose mass through stellar winds, but not so rapidly they become stripped before expanding. They become red supergiants with dimensions measured in thousands of solar radii like VY Canis Majoris. Stars less massive than roughly 8 solar masses follow entirely different evolutionary paths, never producing extreme dimensions. These stars, comprising vast majorities of stellar populations, become asymptotic giant branch stars in late lives, expanding significantly to perhaps several hundred solar radii, but never approaching dimensions of true red supergiants. After shedding outer envelopes as planetary nebulae, these intermediate mass stars leave behind white dwarf remnants, dense balls of carbon and oxygen, roughly Earth-sized, but containing masses comparable to our Sun. Evolutionary paths of low and intermediate mass stars simply do not include red supergiant phases, producing the largest known stellar dimensions. Physical limits on red supergiant size relate to how stellar structure responds to advanced nuclear burning occurring in cores. As cores contract and heat through successive burning stages, envelopes respond by expanding. Expansion continues as long as sufficient energy flows outward to support envelopes against gravitational collapse. But expansion cannot continue indefinitely. Mass lost through stellar winds removes material from outer envelopes progressively over thousands of years. At some point, remaining envelope mass becomes insufficient to sustain further expansion. Stars reach maximum sizes determined by balance between energy generation in cores and mass loss from surfaces. Theoretical models of stellar structure suggest maximum red supergiant radii around 2,500 to 3,000 solar radii for stars, with optimal initial masses and mass loss histories. VY Canis Majoris at roughly 1,420 solar radii approaches, but does not exceed this theoretical limit. Agreement between observation and theory suggests our understanding of stellar structure captures essential physics governing these extreme objects. But theoretical limits carry uncertainties honest scientists must acknowledge. Mass loss rates assumed in stellar models remain imprecise, estimated from observations carrying significant uncertainties. Different prescriptions for mass loss produce different predictions for maximum stellar sizes. True mass loss rates operating in red supergiants might differ from assumed values in ways shifting theoretical size limits. Treatment of convection in stellar envelopes involves approximations potentially breaking down in extreme cases. Convection is inherently three-dimensional and turbulent. Yet most stellar models treat it using simplified, one-dimensional prescriptions. These approximations work reasonably well for ordinary stars, but might fail for the most extended red supergiants, where convection operates on scales comparable to stellar radii. Given these uncertainties, the possibility that even larger stars exist cannot be ruled out definitively. VY Canis Majoris represents the current observational record, but records exist to be broken. Somewhere in unexplored galactic regions or in distant galaxies beyond current observational reach, larger stars might await discovery. The ongoing search for extreme stars continues with increasingly powerful facilities coming online in the current decade and beyond. Ground-based telescopes of unprecedented size will soon begin scientific operations, probing previously inaccessible regions with resolution and sensitivity far exceeding current capabilities. The extremely large telescope under construction in Chile will feature a primary mirror 39 meters in diameter when completed, roughly 4 times larger than the biggest telescopes currently operating. This enormous light-gathering area, combined with adaptive optics systems correcting for atmospheric distortion, will enable observations of stellar populations hidden behind dust clouds thicker than those obscuring VY Canis Majoris. The giant Magellan telescope, also under construction in Chile, will combine 7 individual mirrors into an effective aperture of 25 meters. The 30-meter telescope planned for Hawaii will provide similar capabilities in the Northern Hemisphere. Together, these facilities will survey stellar populations throughout the Milky Way with unprecedented detail. Infrared capabilities on these giant telescopes will prove particularly valuable for discovering extreme red supergiants. The same physics rendering VY Canis Majoris invisible to optical telescopes applies throughout dusty galactic regions where the most massive stars preferentially form. Infrared observations penetrate this dust, revealing stellar populations completely hidden from optical surveys. Space-based facilities will contribute as well, free from atmospheric absorption and distortion-limiting ground-based infrared observations. The James Webb Space Telescope, with its revolutionary infrared sensitivity, has already begun surveying stellar populations in dusty galactic regions. The statistical likelihood of finding larger stars than VY Canis Majoris depends on how common such objects are and how thoroughly we have surveyed relevant stellar populations. Red supergiants represent brief phases in massive stellar evolution, lasting perhaps 100,000 years out of total stellar lifetimes, measured in tens of millions of years. At any given moment, only small fractions of massive stars exist in this phase. The Milky Way contains perhaps 1 billion stars massive enough to eventually become red supergiants. If red supergiant phases last 100,000 years and massive stars live 20 million years on average, then roughly 1 in 200 massive stars currently exists as red supergiants. This suggests roughly 5 million red supergiants populate our galaxy at any given time. We have characterized sizes of perhaps a few thousand red supergiants with sufficient precision to place them in meaningful size rankings. This represents far less than 1% of total populations. If 5 million red supergiants exist in our galaxy, and we have surveyed only a few thousand in detail, statistical arguments suggest we might be missing true extremes of size distributions. Alternatively, VY Canis Majoris might represent true statistical outliers, rare combinations of initial mass loss history, and evolutionary timing, producing dimensions at very edges of what physics permits. In this case, expanded surveys would find nothing larger because nothing larger exists to find. Only continued observation will resolve this question. Each new survey, failing to discover larger stars, strengthens cases that VY Canis Majoris sits near true physical limits. Each discovery of larger stars would demonstrate that extreme stellar populations remain incompletely characterized. The study of extreme stars connects to broader questions about cosmic evolution, extending far beyond individual objects. Elements synthesized in massive stars and distributed by supernova explosions determine chemical compositions of subsequent stellar generations. Enrichment history of the Milky Way reflects integrated supernova activity over the galaxy's 12 billion-year lifetime. When VY Canis Majoris eventually explodes, heavy elements currently being synthesized in its core, along with those produced during explosions, will seed surrounding interstellar medium. This enriched material will mix with existing gas and dust over millions of years, gradually homogenizing through turbulent motions and differential rotation of galactic disks. Future stars forming from this enriched material will contain slightly higher abundances of heavy elements than stars forming from unenriched gas. Planets forming around these future stars will incorporate nucleosynthetic products of VY Canis Majoris into rocky mantles, metallic cores, and potentially biospheres. The philosophical implications of cosmic scale have occupied human thought since ancient observers first contemplated the nature of stars. Each generation discovers new extremes, challenging intuition and reframing humanity's cosmic significance. VY Canis Majoris continues this tradition, revealing that stars can grow to dimensions dwarfing entire planetary systems. The contemplation of such objects produces curious mixtures of humility and wonder, reflecting dual nature of human cosmic awareness. Humility arises from recognizing how tiny human existence appears against cosmic backdrops. We inhabit one small planet, orbiting one average star in one unremarkable region of one ordinary spiral galaxy among trillions scattered throughout the observable universe. Our Sun measures 865,000 kilometers across, seemingly enormous by any terrestrial standard. You could fit over 1 million Earths inside its volume. Yet a single star exists, exceeding our Sun's diameter by a factor of 2,840,000, its volume by factors approaching 10 billion. The Sun, dominating our sky and providing all energy supporting life on Earth, would be an invisible speck compared to VY Canis Majoris. Wonder arises from recognizing that human minds can comprehend these extreme objects, despite never directly experiencing them. We have never visited another star. We have never traveled beyond our own solar system. We have never touched the tenuous atmosphere of a red supergiant or felt warmth of its crimson light. Yet through patient observation and mathematical analysis, we have determined properties of objects 3,800 light-years distant with remarkable precision. This capacity for remote understanding represents one of humanity's most remarkable achievements. We measure distances using subtle angular shifts in stellar positions as Earth orbits the Sun. We determine temperatures from colors of light that stars emit. We calculate masses from orbital motions of companion objects. We infer sizes from relationships between brightness and temperature. Each technique required generations of scientists building on previous work, refining methods, improving instruments, and testing predictions against observations. The infrared observations revealing VY Canis Majoris required semiconductor physics developed in the 20th century, optical engineering refined over decades, and computational capabilities that would have seemed magical to scientists just a century ago. Technology enabling cosmic understanding represents accumulated human achievement across centuries of effort. Each telescope builds upon lessons learned from previous instruments. Each detector incorporates improvements suggested by earlier observations. Each analytical technique refines methods developed by previous generations. The current state of astronomical knowledge represents cumulative effort of thousands of scientists working over hundreds of years. This technological progression shows no signs of slowing despite remarkable achievements already accomplished. Future facilities will achieve sensitivities and resolutions exceeding current capabilities by factors of 10 or more. The cosmic census will expand to include objects currently invisible to our instruments. Phenomena we cannot currently detect will become routine observations for future astronomers. Consider the progression of cosmic awareness over just the past 4 centuries. When Galileo first turned a telescope toward the sky in 1609, he discovered moons orbiting Jupiter and phases of Venus proving Earth was not the cosmic center. Within a generation, the heliocentric model became scientific consensus, displacing thousands of years of geocentric assumption. Over subsequent centuries, astronomers discovered that the Sun is one star among many, that stars are distant suns, that the Milky Way is a galaxy containing billions of stars, that other galaxies exist beyond our own, that the universe is expanding, that cosmic expansion is accelerating. Each discovery extended human awareness to larger scales and revealed new phenomena invisible to previous generations. VY Canis Majoris fits within this progression as the current boundary of our knowledge about stellar dimensions. Future discoveries may extend this boundary or confirm it, but either outcome will add to human understanding. The timeline of human cosmic awareness spans barely 4 centuries since the invention of astronomical telescopes. In that brief interval, we have progressed from believing Earth occupied the cosmic center to mapping large-scale structure of the observable universe spanning billions of light years. We have discovered that our Sun is one star among 400 billion in our galaxy, that our galaxy is one among 2 trillion in the observable universe, that the observable universe may be an infinitesimal fraction of total cosmic reality. The rate of discovery continues accelerating as observational capabilities improve. More astronomical knowledge has been generated in the past 50 years than in all previous human history combined. The next 50 years will likely see comparable or greater advances as new facilities come online and new techniques mature. The personal relevance of such cosmic knowledge varies among individuals in ways reflecting diverse human perspectives on meaning and significance. Some find comfort in placing human concerns within larger contexts, recognizing that earthly problems appear insignificant against cosmic backdrops. The anxieties and conflicts dominating human attention seem less consequential when viewed against scales of stellar evolution and galactic dynamics. Others find such perspectives alienating rather than comforting, preferring to focus on scales where human action matters and human relationships provide meaning. The knowledge that stars can grow to monstrous dimensions does not help solve problems of poverty, disease, conflict, or environmental degradation demanding human attention. Neither response is incorrect. Cosmic knowledge serves multiple purposes for different individuals and need not serve the same purpose for everyone. The universe does not prescribe how humans should respond to knowledge of its scale. That response remains matters of individual choice, shaped by personal values and circumstances. What remains objectively true, regardless of individual response, is that VY Canis Majoris exists 3,800 light-years from Earth, embedded in a rich stellar field, burning with the power of hundreds of thousands of suns, spanning distances that would swallow most of our solar system. This star represents an extreme of cosmic possibility that actually occurs in nature. This is not speculation or theoretical extrapolation, but confirmed observational fact. Multiple independent measurements using different techniques converge on the same basic conclusion. The largest known star, or among the very largest, burns tonight, invisible to human eyes, but revealed through infrared telescopes that see through intervening dust. The light we observe tonight departed this star around the time humans first began experimenting with agriculture, roughly 5,800 years ago. Those photons traveled across interstellar space at the fastest speed the universe permits, passed through dust clouds blocking most companions, and finally reached telescopes recording their presence. Each photon carries information about conditions in the stellar atmosphere 3,800 years ago. The star we observe is not the star as it exists today, but as it existed during humanity's Bronze Age. We look backward through time across a span longer than recorded human history, witnessing a cosmic past preserved in ancient light. In the grand cosmic inventory, VY Canis Majoris is merely one star among hundreds of billions in our galaxy, merely one galaxy among trillions in the observable universe. The star's mass represents roughly 17 to 25 solar masses, trivial compared to galactic masses measured in hundreds of billions of solar masses. Its physical extent, while enormous by stellar standards, spans negligible fractions of distances separating stars. Yet this particular star holds a distinction setting it apart from all others we have found. It is among the largest. This simple superlative applied to a single object among trillions captures something profound about where this star sits within cosmic hierarchy. Records carry psychological weight transcending literal meaning. The tallest mountain, the deepest ocean, the largest star. These extremes define boundaries of possibility, marking edges of what nature permits under physical laws governing our universe. VY Canis Majoris reminds us that the universe permits extremes beyond ordinary imagination. Somewhere in the Milky Way, 3,800 light-years away, a star exists that could swallow our entire inner solar system, including orbits of Mercury, Venus, Earth, Mars, and Jupiter. This is not speculation or science fiction, but confirmed observational fact. The cosmos really produces such monsters, and we, brief creatures on a small rocky planet, have figured this out. We have measured the size of an object we will never visit, never touch, never experience directly except through faint infrared light, reaching our telescopes after a 3,800-year journey. We have extended human knowledge to encompass extremes our ancestors could never have imagined. We have discovered through patience and ingenuity and accumulated technological capability developed over centuries that stars can grow to dimensions spanning billions of kilometers, containing volumes billions of times larger than our Sun. This understanding did not exist a century ago. It exists now because humans chose to build telescopes, develop theories, and dedicate resources to cosmic exploration. This discovery matters even though it does not change daily life on Earth, does not solve practical problems facing human civilization, does not cure diseases or prevent wars or reverse environmental damage. It matters because it expands what humanity knows about the nature of reality. It matters because understanding is valuable, independent of practical application. It matters because we are creatures that seek to know our cosmic context. VY Canis Majoris will eventually die in one of the most spectacular events our galaxy will witness over the next million years. But for now, it burns. The largest known star, or among the very largest, in the observable universe continues converting matter into energy at rates hundreds of thousands of times exceeding our Sun. It continues shedding material into surrounding space through powerful stellar winds. It continues evolving toward eventual catastrophic collapse. We observe it from 3,800 light-years away, reconstructing its properties from ancient photons, marveling at the scale of what nature produces when given sufficient matter, sufficient time, and the right physical conditions. The cosmos contains wonders beyond counting. VY Canis Majoris is one of them, a star so vast that comprehending its true dimensions requires abandoning all terrestrial intuitions about size and scale. Among the largest known stars burns tonight, and we have measured its dimensions, predicted its fate, and placed it within our understanding of how stars live and die. This achievement, however modest compared to cosmic scales, represents something significant in the universe's long history. Matter has organized into forms capable of understanding its own extremes. Atoms that were once part of ancient stars have assembled into beings that can measure the largest stars now burning. The universe has become aware of itself through creatures living on a small planet, orbiting an ordinary star in an unremarkable corner of an average galaxy. That awareness extends now to encompass VY Canis Majoris, among the largest known stars in the observable universe. We know it exists. We know how large it is. We know how it formed and how it will die. We know its place within the cosmic hierarchy of stellar objects. And knowing these things, we are connected to this distant giant in ways transcending physical separation of 3,800 light years. The same physics governing VY Canis Majoris governs our Sun. The same elements comprising that star comprise our bodies. The same cosmic evolution that produced that monster produced the planet we inhabit. We are all part of the same universe, subject to the same physical laws, participating in the same ongoing cosmic story. VY Canis Majoris and the smallest observers are connected through fundamental unity of physical reality. That connection makes the existence of VY Canis Majoris personally relevant to every human being alive today. Not because the star affects our daily lives, but because understanding it extends our conception of what reality contains. The universe is stranger and more extreme than everyday experience suggests. Stars can grow to dimensions that swallow solar systems. Among the largest known stars burns tonight. We have found it. We have measured it. We have understood it as well as current science permits. And in doing so, we have extended the reach of human awareness to encompass one more wonder in a cosmos filled with wonders beyond counting. The journey to understand VY Canis Majoris reveals as much about human capabilities as about the star itself. We have demonstrated that minds evolved on an African savanna can comprehend objects operating under physics so extreme they break our intuitive models of reality. Thank you for joining me on this exploration. If you found this journey valuable, a like and subscribe helps immensely. We have many more cosmic wonders to explore together. And remember, every time you look up at the night sky, you are observing the same universe that contains VY Canis Majoris. You are part of that universe. The atoms in your body were forged in stellar furnaces, not unlike the one burning in VY Canis Majoris right now. You are not separate from the cosmos you contemplate. You are the cosmos contemplating itself. And in that act of contemplation lies something profound about what it means to be human, to be conscious, to be capable of wonder in the face of the truly vast. The largest known star burns tonight, 3,800 light years away. And now you know it. And that knowledge changes you, if only slightly, if only by expanding your sense of what is real and what is possible in this strange and beautiful universe we call home.